That was microphone was off. Sorry. Yeah. I just realized somebody talked. Okay, so let me go back a little bit. We're going to evaluate a double integral, surface integral of this vector field, okay, over the surface. This surface is a closed surface. It is boundary of the solid, half of the cylinder. Hold on, half of the cylinder. Be careful when you read it. It's between. That's a question. It's a boundary of the half of the solid. Be careful. If half of a cylinder, then just only the top piece. Okay. So cylinder usually means it's like a sphere, like the two-dimensional sphere. So it's a solid, a half cylinder. It's a solid, this piece. So the boundary means all of the surface cover, of the solid. Okay, so that's why I have to be 4 pieces. Okay, and then how do you determine the cylinder? This is the inequality given z less than or equal to square root 1 minus y square. So you set z to be that square root of 1 minus y square. Then you get the equation for the cylinder. Okay, yeah. So now you have 4 pieces, 4 surface, which is the boundary of the solid. Okay, then S1, S2, the front and back side, and then the bottom part is going to be x is between 0 and 2, y is between negative and the positive 1, and z is going to be 0. All of it. And then the top one, S4, this is cylinder x squared plus y squared equals 1, or z squared, sorry, y squared. Y squared plus z squared equals 1, z is greater than equals 0. I think that's z is greater than 0, and x is still between 0 and 2. Okay. So that's the 4 pieces. Some pieces, yeah, let's just take a look at the x1. How do you set up an integral? Okay, so for that one, before we use a parameterization, we just needed to look at the normal vector for S1. So normal vector, okay, to the surface is I, okay, in the direction of x positive x-axis. Okay, so the double integral as the surface integral, okay, S d this, right? It's going to be surface in x dot the normal vector ds. Okay, so normal vector is just I has components. So all you have to do is just look at the components, the x square, x square I plus right, y square j plus z square k, the dot product, right? And then only the first component shows up, which is going to be this S1, right? S1. So just x squared ds. But x squared over that surface is 2. X is 2. So that's why S1 is 2 squared ds. 2 squared is 4. 4 times the area of that surface. And then the area of that surface is semicircle. Okay, so it's 4 and pi, because semicircle with radius 1, pi r squared, divided by 2. Yeah, the area of the disk is pi, divided by 2, so it's going to be 2 pi. Okay, and similarly, S2, n still equal to negative, n is a negative I, because it's point to outside. Okay, this is positive oriented. Yes, the surface. So n is I. The reason is why it's negative I is because it's point to that direction. N. Right? The bottom part is n. Point downward. So yeah, you don't need the parameterization here. N is negative I, and so the surface integral S f dot ds, and you will see that the only change here is going to be x squared I, y squared j, z squared k dot negative I ds. Okay, so you are going to get negative S1 x squared ds, because on S2, sorry, on S2, x is 0. So that's going to be 0. So it's 0. Okay, so that part is 0. All right, so the bottom part. So because those are easy to find the normal vector, the bottom part is going to be its downward point. It's negative k. Right? The unit normal vector is always negative k. Right? And then S2, F, S3. So those are the easy part. You can just write down without doing any computation, almost. And negative k, yes. And then only the last term is left, right? And z squared, negative z squared ds. But this is on the xy plane, so z is going to be 0. Okay, the component of z is going to be 0. Negative z squared ds, which is 0. Okay, so only non-trivial part is the integral on the cylinder. Okay, the integral on the cylinder. Be careful. Yeah, an integral on the cylinder. How can I find the normal vector of the cylinder? Look at this picture again. I even don't need a parametrization at this moment. So this is a cylinder, right? Right? Yeah. So at every point x, y, z, this is as a normal vector is from here to here pointed out. So this is a normal vector. I think the normal vector is always at the point x, y, z. The normal vector is always equal to the first component is 0, second component is y, the third component is z. That's obvious. Yeah. Okay. If you draw the normal vector, it's clear. Okay. It is clear that this is going to be unit vector. You know, just like a circle, right? At every point x, y, what is the normal vector? The circle, the vector perpendicular to the circle, which is if it's unit circle, right? The vector at that point, which is perpendicular to the tangent vector, will be just x, y. Okay, so the normal vector is going to be x, y. I just give you an example. Right? It's unit vector and it's perpendicular to the tangent vector. Right? It's actually the vector from the origin to that point, but you move to do that parallelly. All right, so that is then I can write express this without using parametrization right now. Okay, so it's going to be S4, here's x squared I plus y squared j plus z squared k, and then the normal vector will be yk zj yj zk, sorry, okay, yj zk and ds. Okay, finally I got y cubed z cubed and ds. This is a surface integral. Okay, this is a surface integral. Now we have no choice. Okay, we have to parameter the surface. Use the cylindrical coordinates. That's the surface integral right now. It's not no vector here. Okay, no vector here. All right, so how do we do that? We have to parameter the surface, and x is still equal to x at every point. It's like a cylindrical coordinate, but that cylinder is parallel to the x-axis. Y equals, let me draw the picture. Y equals this is theta, right? Y is this is sorry. This is y-axis. This is z-axis. This is my angle theta. So y is going to be cosine theta because radius is 1. Z is going to be sine theta. Okay, theta is between 0 and pi. It's half. Right? So the parameterization x and the theta is going to be x cosine theta, sine theta. Okay. And then you need to x, yeah, x is here, x is between 0 and 2. So theta between 0 and pi, x is between 0 and 2. That's a rectangle. And the rectangle is mapping to the semi-cylinder. Is mapped onto the semi-cylinder. So use a rectangle to describe the semi-cylinder. Okay. And I hope we still remember the Jacobian. Otherwise, we have to do the computation like that. So 1, 0, 0, and r theta is going to 0, negative sine theta, cosine theta. Okay, and I'm going to look at the cross product. Who has a question? Okay, yeah. All right. So let me write down this. I'm going to quickly, yeah, it's a cross product. How to do cross product? So save my time, I just put the I, J, K on the top. It looks like a matrix. Okay. So I is going to be blah, blah, you know, it's going to be 0. Okay. Clearly it's 0 because this is a perpendicular to the cylinder. And the J, the first rule, and that'll be negative cosine theta. Okay. And the K is going to be negative sine theta. Okay. So this is a normal vector perpendicular to, okay, the point is that this normal y that's negative sign here, it's actually pointing inside. This is perpendicular to the surface anyway. But the reason is maybe the orientation, you know, r theta can, if we switch it, then it can become positive. But anyway, so this is going to be 1. Okay. Right. So the surface integral is 4 y cubed z cubed ds. Remember, this is going to be the integral, double integral of d. D is as x is between 0 and 2, theta is between 0 and 2, 0 and pi. And then you plug a y. Y is a cosine cube theta. Z is a sine theta. And then the Jacobian is going to be 1. So just dA, okay? Yeah. So all I have to do is just evaluate this integral. And this will be the double integral. Right? And dr. So you can, all you have to do is evaluate that integral. Okay? Do you know how to evaluate this integral? Yeah. Cosine.
Actually, I had that.
Oh, you're missing the 2 pi.
I was just missing
The S1, the integral on S1, right?
yeah,
The first one.
the S1.
Okay, cool. But that takes lots of time, you see what?
Yeah.
Yeah. So, yeah, just evaluate this integral and this will be true. I'll stop it here, okay? But anyway, so this is yeah, cosine cube theta, you have to use a substitution, okay? Use substitution, cosine. The idea is that cosine cube theta is going to be cosine square theta cosine theta. Cosine square theta is 1 minus sine square theta cosine theta. Okay, this is the idea to evaluate integral. Okay. All right. I'm going to, yeah, we should. I'm going to talk about today's theorem, but let me summarize things. Okay. In calculus, the fundamental calculus is going to be this integral. The fundamental theorem of calculus is going to be f of x evaluated at the endpoints. Okay. Then after that, you have to define the line integral, right? You have the line integral. You know, we begin with the line integral s, c, c, and f ds, right? After you use the line integral, on this side, we have as a surface integral s and f d, let's use a ds, okay? Capital ds, because on the s, okay? After you use a line integral, we have line integral vector field, dts, okay? But this is usually is denoted by another notation, dr, okay? So for some reason, maybe we should use dc, okay, because R means it's you already have a parameterization. Okay, so it's not the best notation, but then maybe there's no choice. Okay, so T is a unit tangent vector of the curve. If I draw the picture, so this is a curve C, and the vector field I'm going to use a red color. Okay, and this is F, and at every point you have a unit tangent vector, right? So unit tangent vector, then you can tell. But on the other side, here's a sphere. You can, once you define the surface integral, you also can define as the vector field times inner product ds. Okay, but this also denotes another notation is d dot ds with the arrow symbol on that. Okay, so this is the normal vector times the surface element. So if you look at the picture, this is surface S, right? This is C, right? And this is a normal vector and unit normal vector, right? You know, we're trying to understand those terms. This is just integral, nothing about the surface in fundamental theorem of calculus. Okay, so the vector field is going like that, right? F. So the inner product at every point is a function. So then the function can integrate it. Okay, so that's the summary. Then we have the so-called fundamental theorem of calculus for the line integral. For the line integral, for the line integral, I'm going to, we generalize above theorem, this theorem, to a high dimension case, okay? So this is a end point is 0 dimension, left side is a 1 dimension, okay? It's line integral around the curve, and this involves the derivatives. So now I have a line integral, okay? And we find out if this is a curve around some surface, right? So it's hard to draw it. Okay, so this is a surface. Then I have a closed curve C. Okay, if I have a closed curve C, then we have the following Stokes theorem. Okay, the Stokes theorem says that you can integrate. Where's the Stokes theorem? Right, so this is a, okay, so this is a piece, right? And a vector field is in across the surface. It can be on the surface, yeah. So this line integral, right, and f d ts or ds, dr. Okay, let's say dr, right, can be changed to the surface integral. Here's s. Okay, and then this will be the curl of the vector field ds, the dot product. So compared to the integral here is going to be f, capital F, maybe evaluate at 2 endpoints. Okay, see, you involve the derivatives, right? The same, you involve the derivatives. Okay. So endpoints here, just 2 points here. The endpoints form this curve, the endpoints of this region. Okay, on the surface. Yeah. So now, what happens to here? Can we have a similar theorem? But this time, this is a closed curve. We have to talk about closed as a closed surface. Okay? A closed surface, inside a closed surface, you know, you have a region E. Okay, E is a here E is a enclosed by the surface, closed surface S. Okay, then what I can say that is this surface integral S compared to the unclosed surface, okay? And the left side is line integral on closed curve. You know, we just go one dimension higher. And that's F ds, okay? And this can be also translated to the integral over the region enclosed by the surface. And this time the vector field is just ds and dv. It's interesting. All right. Now it's not exactly similar to the one Stokes theorem, right? Stokes theorem here is a product vector. The reason is because we live in three-dimensional space. We only consider the flat three-dimensional space. So that's the reason. That's the reason, you know. Just the what I should say. I'm trying to find the comparables too. It's a slight difference. You see, the first part is okay. The surface integral vector field out of a closed surface, but why here is not a, you know, just usual triple integral, right? In dv, but here why that's surface integral? Because we can easily visualize the surface in three-dimensional space, a curved surface. So we can state the theorem a little bit more general here, closed curve on the surface. Okay, then you get this theorem. But imagine our universe is curved, right? You believe that, you heard about that. Okay, then this theorem can be stated in more general case, but it's hard for us to understand. We assume our surface, our space is a flat. So that's why this surface integral on closed surface is going to be like that. You know, here, if you only consider the two-dimensional case and just in the XY plane, suppose you are the animal just living in two-dimension plane, right? And then you will see that you still have a vector field in two-dimension plane, right? This is a vector field. Whoa, the vector field change color. Okay, but this two-dimensional vector field, and the theorem is still can be stated like that. C, then it's easy, you know, do the comparison here. And dr, still dr. But this time will be, I put a d here instead of a surface, d, okay? And the curve of the vector field is nothing but, I still can use the curve of the vector field. Dot product was the third dimension, dA, okay? So that's a dA. You see, compare them, they're similar. But this one, it's called the Green theorem in dimension. This is a Green theorem. Okay, in dimension 2. So you can also view that one as the Green theorem in dimension 3. Okay. Yeah. So those two can be compared. Okay. These two can be compared. And if you put more details here, if F is P and Q, right? Then this integral will be like a P dx Q dy, and the right hand side is D, and I think this is going to be Qx minus Py and dA. Okay, so yeah, very similar to yeah, we're trying to compare those two. Okay, I'm trying to compare those two theorems. This is called divergence theorem in three-dimensional space. Let's understand this. All right, so let's go back a little bit. Those two statements are not exactly the, you know, in two-dimension, three-dimension theorem. They're not exactly, you cannot compare. Just say the divergence theorem is a version of Stokes theorem in high dimension case, no. And actually is the special Stokes theorem, which is Green theorem in high dimension, because the whatever enclosed by the curve here is a flat, and this E, the region E enclosed by closed surface is also, we assume it's a flat. Okay, we assume our universe is flat. Okay, Fred. Okay, you cannot see that it's curved because you live inside. It's almost impossible to see it's curved. Okay, so we have this special divergence. But if you want to state more general divergence theorem, then the statement would be not like that. Okay, but that's all we need. Okay, so divergence theorem is a generalization, is a green theorem in three-dimensional case. Okay, and green theorem can be generalized to vector field over surface, then that is the statement. So we do not have exactly the same version of the theorem in three-dimensional space because it's beyond our imagination. Okay, if we will view our universe, three-dimensional space is a curved, surface in four-dimensional space. Then you understand. Okay, then you can have a similar version, okay, of the theorem, of the Stokes theorem, okay, but that will beyond your imagination. Okay. So because our human being lives in three-dimensional space, it's hard to imagine four-dimensional, five-dimensional. All right. So that is a Stokes theorem. That's called divergence theorem, and let's do some exercise. Okay. So you have options right now. If you are given the problem, we see. Remember, we did it right. There's a ceiling. Let's go back to the problem here, because this is a closed. Yeah, that's right. So section 16.731. Okay, let's do this problem. Okay, so again, S is going to be x squared I, y squared j, z squared k. S is the boundary of the solid. Okay, the solid is z greater than, and x is between 0 and 2. Okay, so this is a good example to applying the divergence theorem. All right, so let's do this problem. Now, what I did above, right, is we have to evaluate the surface integral over 4 pieces of 4 surfaces. But this is a solid. Right? This is solid. Right? For this solid, yeah, here's a x-axis, y-axis, z-axis. Okay. Okay. So I call the solid, let's call it E. Okay, how about like that? We use a notation, right? According to divergence theorem, this surface integral F, okay, and ds, right? So definitely the orientation will be the normal vector point outside. Okay, that's by the default. Okay, let me double read the problem. Yeah, it does not say that. Usually, when just a boundary of the surface, the boundary of the solid, that means that surface, the normal vector is point outside, the unit vector point outside, because there are 2 options for the normal vector, right? So according to the divergence theorem, is going to be the triple integral, which is inside E, right? Divergence of F dv. Wow. Okay, so simple. Because it's the surface closer. All right, so let's find the divergence. The divergence of F is going to be the partial derivative of x squared, the first component, partial derivative of y squared with respect to y, partial derivative of z squared with respect to z, and dv. Okay, so you will get twice of this will be x plus y I think it's plus z and the dv. Right. Wow, that's much simpler. Okay, then this is a triple integral. How do you do that? The triple integral can be changed to the double integral, right? You can take, let's assume this is a d. The bottom part is d, right? So assume that this is a d, okay? D is going to be in the xy plane. X is between 0 and 2, y is between -1 and +1, right? At every point, you get a z, the surface, right? Which is z. So you have a double integral dA, okay? And then the value for the z is from 0 to square 1 minus y squared, okay? X plus y plus z dz. Okay, how about like that? I'm not sure where we can easily do this problem. Yeah, we have to parameterize that. All right, so evaluate with respect to z first. Okay, and then the antiderivative of this function would be x plus yz plus half of z squared, and evaluate at this end point. Okay, so I'm going to get x plus y plus half of 1 minus y squared and then dx. Okay. Then I'm going to get the double integral, the iterative integral. X is between 0 and 2, and the y is between 0. I don't know which one should be evaluated. I think I should evaluate with respect to x. Y is from -1 to +1. X is from 0 to 2. Dx, dy. Okay. All right, so the antiderivative of this will be half of x squared plus yx, right? And then square root of that, and half of x antiderivative. So I put the 2 there, I got 2, okay? 2 square over 2 plus 2y. And then I put the 2 here as just equal to 1 here, 2 over 2, so it's 1 minus y squared and dy, okay? Are we able to evaluate this integral? I think we can. It's a little bit complicated, okay? Yeah, there's 3 terms. I think, yeah, you have to evaluate one by one. So this is going to be 1 minus y squared dy, right? And plus 4 dy, and plus 2 -1 2. Okay. I think the one in the middle, you don't need to waste time because it's other function. I integral from -1 to +1, right? So this is going to be 0. You only have 2 terms. The second term is easy. The first term, do you still remember how to evaluate? Right? It's 1 minus y squared. Okay, you have to use the best way to do is use trigonometric substitution. Okay, so actually what you get here is a semicircle area, right? Because imagine this is the integral, right? This is y-axis, this is z. Okay, so if we want to find the area of this semicircle, what do you do? From negative to positive, right? The area of the semicircle is going to be the integral of the graph, right? So the area is going to be from integral, right? It's 1 minus y squared dy, right? So that's it. So I don't need to do anything here. It's a 4 times pi over 2. Okay. Then the second one, I needed to find the antiderivative function. Okay. I get here 2 pi. And the double it, it's going to be, oops, where's my file? Right. So I get, actually I get 4. Okay, 1 minus 1/2. Okay. So it's 2 pi. I think it's 2 pi plus 2. It should be the right answer. Yeah. Okay. So that's it. So this is a power of divergence theorem. It's very useful. Yeah. Okay. So I view the divergence theorem as a general the high dimension version of the green theorem. Green theorem is have a closed curve, make sure closed curve, okay? And it includes a domain in the xy plane. Then if you have a line integral, you just change it to double integral. But here you have a vector field over the surface includes a solid. Then if the integral, the surface integral of the vector field, right, can be changed to the double integral, the triple integral of the divergence of the vector field. Okay, divergence vector involves partial derivatives. Okay, so let's go back to this problem again, right? So the surface is not necessarily be smooth, as long as it consists of several smooth pieces, smooth surfaces, like this one. It consists of 4 smooth surfaces, okay? And 2 semicircle kind of, right? One cylinder and 1 rectangle. Okay. Then you can change it to this surface integral to a double integral. Right? Now, if you ask me, do we have the version of the theorem in high dimension case? Yes. On a curved 3-dimensional space, yes. But it's hard to imagine curved 3-dimensional space. Otherwise, you can understand Einstein theory. Everybody knows Einstein, okay? Even kids. I think first grade already know the Einstein, but nobody knows what is Einstein. Okay, very few. Okay, on this campus, if you randomly find any professor or any guy, only maybe you meet one person can really explain to you what is Einstein did in his paper. That's when Einstein published his paper. Only in the whole world, only 12.5 people understood his theory. Okay, that was the story. That's true. Yeah, even these days. Okay, maybe you walk through the department of physics, knock all the doors, and ask them to explain to you what Einstein did. Maybe one professor probably can explain to you. Okay. But if we went to Blooming, that was an institute of advanced study, something like that, and that was a group of people working, just specializing in this area. Okay. All right. So let's continue. All right, so our next problem, I want to do, yeah, let's understand. Find the, so the vector field is going to be just x, okay, so going to be at every point, the vector field x, y, z is going to be z, y, x. I just switched to 2 variables. It's not the radiant vector point outside, okay? And then there's a twisting here. Okay, it's hard to draw this vector field. Understand? Okay, so the surface is going to be the sphere. Okay, the sphere. X squared plus y squared plus z squared equals 1. Okay, and evaluate this surface integral. Okay, this also in physics called the flux of F. Okay, across or over the sphere. Okay. Yeah. Right. So good. The surface is a closed surface. We call it closed. So it's not like a upper hemisphere. Upper hemisphere is a half of the sphere. Okay. It's not closed. It does not include the solid. But this sphere includes a solid. That solid in mathematics is called a ball. Okay, that was the difference between ball and the sphere in mathematics. Sphere is only two-dimensional object. Okay, so when you cannot say find the volume of the sphere because that's not precise in mathematics. Find the volume of the solid enclosed by the sphere, okay, or find the volume of the ball, okay, with radius r. Okay. All right. So because it's closed surface, right? This is a the sphere. By default, the normal vector is this. Okay. So this is actually going to evaluate this f dot and ds. Okay, that's what we want to evaluate. So we have a couple ways to do. You can evaluate directly, right? Or you can use a divergence theorem. Maybe it's not too bad to evaluate directly, but it's an inner product of the vector field with the normal vector. It's a little bit strange. It would be zx. Yeah. Okay. So we can. If you want to evaluate directly, you can do that. Okay. How do you do that? Use the spherical coordinates, have to parameterize the sphere, okay? And then evaluate. It's complicated, it takes much more longer time, right? But we can change it to, this is the ball inside, B means the ball enclosed by the sphere. We can change to the triple integral of the region enclosed by the sphere, the divergence of F and dV. Okay, dV is just the volume element. Okay, so when I find the divergence, the divergence is going to be partial derivative of z with respect to x, partial derivative y with respect to y, partial derivative x with respect to z. Remember? Okay. So this is a vector field z, y, x, then the corresponding partial derivative, the divergence. And so this is going to be just the y. And that is going to be the volume of the ball. And the volume of the ball is 4 pi over 3. Okay. Now, if you do not want to use divergence theorem, it's pretty complicated. Let me set up an integral, maybe show you, okay? If we do not use the divergence theorem, sometimes we cannot. For example, it's just half of the semisphere, right? If you do not use it, and then we have to parameterize the sphere, which is phi and the theta. And I remember this will be sine phi cosine theta, sine phi sine theta, and the cosine theta. Okay? And 100% sure, okay, this will be the same number. Okay, it's a normal vector, it's unit normal vector. It is pointed to, it is actually pointed out to, we can use permission directly, but you can, it's the same, right? Now, if you use this formula, hold on. If you use this formula, f dot ds, you have to evaluate the surface integral over the df and here r phi theta, then right. If you use this formula, then you have to do the cross product. But I already gave you the formula for cross product. My suggestion is we are not going to use this formula for this particular case, because otherwise you have to find a cross product, takes waste a lot of time. So what I'm doing is I use a spherical coordinates later for the surface integral, not for the integral of the vector field over the surface. So I give up that. I know for the sphere, right, at every point x, y, z, this normal vector is going to be x, y, z again. Okay? So the surface integral, by definition, is the inner product of this, right? So f is y, f is going to be, at that point, f is going to be zyx, remember? Yeah, at that particular point. At the point x, y, z, and n is given by this, f is given by that. All right, so the inner product of them will be xy, y, and zy. So actually, the surface integral of twice of xz plus y squared. And the ds. Oh, I forgot the sphere element. You know, if you use the sphere coordinates, you have to memorize this. Yeah, you have to memorize the length of the cross product. Yeah. Yeah. Let me check this. Okay, this may be not true. Okay, so I'm going to. We're going to. Yeah, Professor Phil should memorize this. So let's double check. This is a perpendicular to that vector, but maybe there's a factor there. Okay, I'm going to double check. All right. So let's calculate this. This will be a cosine phi, cosine theta, cosine phi, sine theta, negative sine phi. Theta will be negative cosine sine theta, and sine phi, cosine theta, and 0. Okay. Then in order to get the cross product, okay, I will get the first one negative, because it's positive sine phi cosine theta. Then I get it's negative it's become positive sine square phi sine theta. Okay, then the last one cosine phi sine phi. All right, so that's what I got. Okay, so it's not a unit vector. So there is a fact sine phi, it can take it out. This will be normal vector. Okay, this is a normal vector. Okay, so I have a missing one term at the very beginning. I want to show to you here's sine phi. Okay. Anyway, so it's up to you which part you're going to use. If you want to use this formula, then ds is a norm of this, and dA. Okay, ds dr d phi d theta. So the norm of this is just sine phi. Okay, dA. So that's what I need. Right, then then you have to, the surface integral f ds is going to be the double integral, right? Double integral d. I'm not going to mention the range between for the phi and the theta. So 2x times z. What is x times z? X is going to be sine phi cosine theta. So sine phi, z is cosine phi. So cosine phi cosine theta. Y is going to be sine phi sine theta squared. Okay, then dA. Then sine phi dA. Okay, so this is a x times y, 2xy, 2xz plus y squared. So y squared is y is going to be sine phi sine theta, and x is sine phi cosine theta, and then z is cosine phi. Okay, so you have to evaluate this double integral. It's pretty complicated, but you can do that. Okay, so let me write down this integral from 0 to pi, and from 0 to 2 pi, right? And I can take sine phi out. It's 2 cosine phi cosine theta, and sine phi square sine theta, and sine square phi d theta d phi. Okay, I'm not going to evaluate this integral, but you can do that. But you see, it's complicated. If you're given the problem, ask you to evaluate the double the surface integral of the vector field. If you go ahead to use the formula, direct formula, is parametrization, and it's complicated. Okay, it's not easy to get right answer. It takes a much longer time, and you have to compute it. If you don't remember for the spherical coordinates, if you don't remember ds, what is ds, then you have to do computation for that one. Okay, and then you find that no space left. There's a why the strat doesn't give me too much space. I need more. Okay, because you are doing it the wrong way. Okay, they're only about 1/3 of the page for that particular problem. Okay, that's not. You see, it takes so much space there, right? There's a whole page. Okay, so this is a. We stop here. We don't want for closed surface. Yeah, for closed surface, you have to look at, you have to transfer the surface integral to a triple integral over the region enclosed by this surface. Okay. And sometimes if I give you a problem on the, if I give you a problem, I really want to use a divergence, it depends on the problem, okay? If I change it to this one, x, y, z, just a special vector field, y, z, right? At every point, and this is x squared plus y squared plus z squared. You can compare which one is easy. Evaluate the surface integral for f and ds, okay? Now, in this particular case, probably it's easier not to use the surface integral, the divergence theorem. Why? Because the first method you compare, right? That's a special case. For the sphere, at every point x, y, z, the normal vector is given by x, y, z. Okay. So f dot in x, y, z. F is going to be x, y, z, right? So what you do is just get x squared plus y squared plus z squared. But x squared plus y squared is going to be 1. All right? for the point on the sphere. So this surface integral ds is nothing but, okay, and that's going to be surface integral 1, which is the area of the sphere, which is 4 pi. Then very, very quick. It's enough space, just a little bit. Okay? Because it's so easy to compute the inner product. Okay? The second method, you use the divergence theorem. All right, because the sphere includes a solid, which is a ball, right? So then the surface integral is going to be the triple integral of ball and divergence of f dv. The divergence of f is a constant. This partial derivative of x, partial derivative of x, plus partial derivative of y, or partial derivative of z with respect to z, and then dv. Okay, it's 1, 1, 1, so 3. It's going to be 3, okay? Which is 3, the volume of the ball. The volume ball is going to be 3 times 4 pi over 3. Radius is 1, so it's 1 cube. So the answer is still 4 pi. You see that? It's the same answer. Okay, so for this simple one, simple example, it doesn't matter which method you're going to use. All right. Right, so let's do problem number 13 from the book. F is going to be the absolute R times R, where R is going to be X, I, Y, J, and Z, K. Okay, so this, well, this is the same direction of X, but it's getting, F is just getting longer and longer. Okay. S consists of the hemisphere, z equals 1 minus x squared minus y squared, and the disk, x squared plus y squared less than 1 in the xy plane. So step 1, draw the graph for the sphere. We just have this kind of sphere, right? Semisphere, and this is a semisphere. Oh, it's bad. Right? And this semisphere, wait a minute, with radius to work. So the cylinder is above, and the disk is this. Right? So this is the whole picture. Okay. The disk is the bottom part of the hemisphere, the bottom hemisphere. So it's closed surface. This is S. S is closed, very important. If S is not closed, you cannot use divergence theorem. If S is closed, then what is inside called E, right? Okay. So evaluate the surface integral of F and ds. Because let's try. Yeah, we don't have a time. We'll just use divergence theorem. Otherwise, you can. I have a two. It consists of two surfaces, right? And I evaluated on each of them. I think I can do that. It's not that complicated. Okay. And for this particular problem, you still have two options. Okay, if you use the divergence, this is going to be E divergence of F and ds dv. Okay, so divergence of F. How do you calculate divergence of F? Well, that's tough. Okay, divergence of F in the space. F actually is going to be actually square root of x squared plus y squared plus z squared. And here's xi plus yj plus zk, remember. Okay? Yes. So the three components, I have to calculate one by one, right? So let's look at the partial derivative of x of this. Okay? And with respect to s, is that similar to the other one? Okay, first of all, you get this. Second, you get x, and the square root of x squared plus y squared plus z squared, then 1/2, and you get 2x. Okay, so x 2 cancel out, I get x squared. So if I get x squared, I get this. Here's if you combine them, you get x squared plus y squared plus z squared. I get x squared. Okay. Now, if the middle one, I get a y squared. The last one, I get z squared. Okay. So the divergence of F is going to be square root x squared plus y squared plus z squared. And I have three terms like that. 3x squared plus y squared plus z squared. Okay. And then I have x squared from the first one, y squared from the second, z squared from the last one. So you have 4. Okay. So after you simplify, it's going to be 4 square root x squared plus y squared plus z squared. So you can do that. Okay. So divergence. I think use the divergence theorem. It's easy. So it's a triple integral of the region E. This is the region under the hemisphere. Right, and this is going to be divergence of F dv. All right, so now you have to use the spherical coordinates to evaluate. Okay, so use the spherical coordinates. I think I is from 0 to 1. Phi, that's dr. You can use I think use a row. Let's use a row. Okay, then d phi. So phi is from 0 to half a pi. Then you have d theta. 2 pi d theta. Okay. Then what is inside is 4. This will be rho, and I think a rho sine phi. That's all we hear. Okay. And evaluate one by one. This is from Jacobian. This is from a square. Rho is a square x squared plus y squared. Okay. So the first thing you get is going to be 2 pi times 4 is going to be 8 pi. Okay, then you evaluate sine. Sine is going to be cosine t negative from 0 to pi over 2. So negative, it's just 1. Okay, then you find the antiderivative of this row and get a 1. It's 2 pi. Okay, so 2 pi is answer. But I don't have a time right now. I can also evaluate this this integral over the surface, which is this hemisphere and the disk. Okay, but in that case, the normal vector is easy to compute, so it's not that complicated. You will get 2 pi quickly. Okay, so you can also evaluate this surface integral using another method. There's a traditional method, yeah. Before we learn the divergence theorem. All right, let's stop here, and we are almost end of the semester. Okay, we have one more lecture to cover.